want to look at the application problem that we looked at in section 14.7. It was problem number 50. We did this at the end of 14.7 using the techniques from 14.7. I want to now take a look at how we can use Lagrange multipliers. Okay. So we're finding the dimensions that will maximize the volume of a rectangular box if the surface area is 64 square centimeters. So the volume is just a function of three variables. It would just be x times y times z. Okay. And our constraint is that the surface area, which I'm just going to call A, has to be 64. But we've said that the surface area is just 2 copies of xy plus 2 copies of yz plus 2 copies of xz. Essentially x times y, that's giving me the bottom and the top. Y times z, that's giving me the front and the back surface, and x times z, that's giving me the left and the right sides. And if I want to, I could simplify this a little bit. I think I'm going to instead work with 32 equaling xy plus yz plus xz as my constraint. So this isn't the area anymore, so I'll just call that g of x, y, z. That's giving me my constraint. Now, when I introduced this problem, I mentioned that we were trying to maximize this function of three variables subject to this constraint, which essentially amounts to a level surface for this function of three variables, and that section 14.8 was going to be all about doing that. Okay. There is one interesting twist to this problem, though, because there's another restriction I have on the domain. The constraint always puts a restriction on the domain. I can only plug in values for x, y, and z that make this equation true. But this is an application problem. X, y, and z are dimensions. They have to be sides, legitimate side lengths for a rectangular box. They cannot be negative. In theory, x, y, or z could be 0. That would just give me a degenerate box. And I'm actually okay with that idea because I know that's not what I care about. That's not going to maximize volume. If any dimension is 0, the volume is 0. But I'm not allowing negative values. This equation can certainly be true if some of x, y, or z are negative. Okay? As long as the net result ends up being positive, I'm fine. So I'm introducing some additional constraints on my variables. Is that going to mess up my problem, or is that going to make it easier? In this particular case, it's going to make it easier, but in other cases, it could mess things up. Okay? Because essentially, in introducing, I want a plane here. Where's a plane? Ah, I had misplaced my plane. I apologize. I found my plane. Okay. If this is, let's just say we're looking at the YZ plane, and I'm introducing that as a barrier and saying we've got to be in front of that because otherwise, if we're behind the YZ plane, x would be 0. Well, if I had some function that was increasing as I got closer and closer to this plane, it would be possible that my maximum would occur on that boundary surface. Or if I'm not including that there would be no max because I would be getting closer and closer to a high point, but if I'm not including points on that boundary, then there is no max. It can absolutely mess up my problem if I introduce additional barriers. In this particular case, I happen to know that on all three coordinate planes, if I allowed x or y or z to be 0, the volume would be 0. So I know I'm not approaching a max as I'm approaching that from anywhere in the first octant, which is where x, y, and z would be 0. So in fact, since I know that the volume is 0 at those places, I know as I'm getting closer to any of the coordinate planes, my volume would actually be decreasing to 0 because it's positive in the first octant and it's 0 on any of those coordinate planes. So because of that, I can say, okay, I'm not going to run into a problem with my max actually occurring on one of the coordinate planes, and then I have to decide, am I including those points or not? Or there being no max because we're increasing, we're not including the point on the boundary, and so we're just getting bigger and bigger and bigger, but not actually hitting that maximum point. Okay, we're not going to have that problem here. So I'm going to use Lagrange multipliers and, as an added advantage, have this practical constraint, which is that x, y, and z are positive. So I'm basically going to be saying I'm looking for solutions to the system of equations I get using Lagrange multipliers, but I'm only looking for solutions where x, y, and z are positive. That's going to be nice. Okay, so let's take a look. Now notice my constraint is an equation, not an inequality. So I'm just working with points that are on this constraint surface. I don't need to check critical points for the volume as well. If my region that I was working on was described by an inequality, I would have to check critical points directly and then just also use Lagrange multipliers on the boundary. Okay, but here I'm just working on a constraint equation. I'm just going to use Lagrange multipliers. So the gradient of v, well, the partial with respect to x will be yz, the partial with respect to y will be xz, and the partial with respect to z will be xy. Cool. Okay. I will just mention, because it's a good exercise, if you do find the critical points for this, it turns out the critical points are all points where 2 of the 3 variables are 0. So a good exercise to maybe just confirm that. Okay. All right, the gradient of the gradient of g, because I'm not working with a, I'm working with g, which is half of a. Okay. The gradient there, let's see, the partial with respect to x is going to be y plus z. The partial with respect to y is going to be x plus z. And the partial with respect to z is going to be y plus x. Okay. And that is not going to equal 0 for this particular problem. Okay. I know that that will not equal 0 for this problem because I've got the added restrictions that x is bigger than 0, y is bigger than 0, and z is bigger than 0. Those are the practical considerations that I have because this wasn't just a math problem. This was a math problem where x, y, and z represented lengths of things. Okay. So if they're all positive, the sum of 2 positive numbers is never going to be 0. Okay, fabulous. So, let's see. I can now say I'm looking for places where the gradient of v is lambda times the gradient of g. So that would mean yz, xz, xy is equal to lambda times y plus z, x plus z, y plus x. And if I just do that scalar multiplication, that's lambda times the quantity y plus z, lambda times the quantity x plus z, lambda times the quantity y plus x. Fabulous. Okay. I'm going to erase this information that x, y, and z are positive, but I'm not going to forget it because it's going to be useful. Okay, so equation 1, my first components have to be equal. So y times z is equal to lambda times y plus z. My second equation, second components have to be equal. So x times z is equal to lambda times x plus z. My third equation, third components are equal. So x times y is equal to lambda times y plus x. And then my fourth equation is just the constraint, which was that xy plus yz plus xz is 32. I don't remember what order I've written these 3 terms in before. I may have juggled the order of them, but it doesn't matter because addition is commutative. Okay, so we are looking to solve this system of equations. So, I'm want to try to solve for lambda. What could go wrong? Could y plus z be 0? Because that's what I want to divide by. And the answer is no. Because if y plus z is 0, either they're both 0, and I know my maximum won't occur there, or one of them's positive and one of them's negative, and the practical considerations say, no, I'm really looking just in octant 1 where they're both positive. Okay. So, because I know I'm only looking where all my variables are positive, y plus z, x plus z, y plus x are all not 0. Okay. So I'm just going to make a note. Okay. Since x, y, and z are positive, so are y plus z, x plus z, and y plus x. So I can actually divide by all of them. Now, if I were just doing this as a math problem, not a practical problem, I would not be able to make that assumption, and I would have cases. Okay. But if I'm doing this as a practical problem where I'm just looking in octant 1 where x, y, and z are positive, and I've confirmed that those coordinate planes that are going to be the boundaries of octant 1 don't mess things up, because on the coordinate plane my volume is just 0, and I know it's positive everywhere strictly in octant 1, so there will be some max in octant 1. The boundaries that I've introduced don't mess that up. And the fact that there is a max, we sort of talked about at the end of the last section, that's a little bit common sense and a little bit just, I'm giving it to you. There is a max. Okay, so let's see. From equation 1, I can solve for lambda. So lambda is y times z over y plus z. From equation 2, I can solve for lambda. So lambda is x times z over x plus z. From equation 3, I can solve for lambda. So lambda is y plus x, is xy over y plus x. Great. So lambda equals lambda equals lambda. So yz over y plus z is equal to xz over x plus z is equal to xy over y plus x or x plus y, either way. Fabulous. Probably don't want to work with all three characterizations at once, but let's just pair them off. If I pair off those first two, yz over y plus z is equal to xz over x plus z. Now if I cross multiply, I'm going to have yz times x plus z is equal to xz times y plus z. Let's distribute. xyz plus yz squared. As I multiply things out, I'm just going to rearrange the variables if necessary so that they're always in alphabetical order, just because that makes my life simpler. Okay, and that's going to equal xyz plus xz squared. Okay, now I can subtract the xyz from both sides, so yz squared equals xz squared. Because I'm working in octant 1 where z is positive, I can divide by z squared, so y is equal to x. Pretty nice. Okay, we're nearing the end, but we've got a little ways to go and this video's been going for a while, so I'm going to stop the video and we'll finish this in the next video.